Warm greetings to everyone. Today we are going to see about the for a axial loaded tensile or compression member which is subject to a load W along the axis of the body. So how will you find the stress, then strain and the deformation of the axial loaded member? For example, I am taking a member which is subjected to the axial pull along the longitudinal axis. Now what will happen? Definitely there will be a deformation along the length of the body, and also the lateral dimension also gets changed. So in the case of the change in length of this member, that is a pen, is determined by the value of delta L is equal to W into L divided by AE. So which is a elongation, that is the increase in length will be taken place, where W is the applied axial load on this body, L is the length of the member from beginning to end of this body, and A is the area of this body. So it is a circular in cross section, means pi d square by 4, and E is the Young's modulus of the material of the body. So that value depends upon the material to material. So the deformation or the change in length, that is here increase in length, will be taken place. That is delta L is equal to W into L divided by A into E. It is in the unit of millimeter or meter. If it is a tensile, definitely increase in length, use the positive sign. If it is a compression member, that is if you are applying a compressive load on this body, where capital P is equal to compressive axial load applied on this body. Here also the decrease in length will be taken place, but the lateral dimension gets increased. So because of the compression or the pushing load. So therefore here the decrease in length or delta L is equal to P into L divided by AE. So here you will get the change in length as negative sign because of the compressive load, so there will be a decrease in length. And you can able to find the change in diameter by using the lateral strain, epsilon lateral or E lateral, that is equal to change in width or change in diameter divided by original width or original diameter. So delta D by D or delta B by B, you can call it. So in the case of a number of elements are there in a given axial loaded member. For example, it is of composite section. There are three parts, right? L1, L2 and L3, but I am applying the same axial tensile load on this body, but due to the different cross section and different Young's modulus, we have to use the delta L or increase in length if you are applying a tensile load. Delta L is equal to P1 into L1 divided by A1 into E1 plus P1 P2 into L2 divided by A2 into E2 plus P3 into L3 divided by A3 into E3. Because the length of each part and Young's modulus of each part and the area is also a different one, means that's why I call it as the different load, means P1, P2 and P3. If loads are equal, capital P is equal to capital P1 is equal to capital P2 is equal to capital P3. Then Young's modulus of different three cross sections are capital E1, capital E2 and capital E3. If it is equal, all the capital E Young's modulus is equal to E1 is equal to E2 is equal to E3 for the different sections. So from this equation you can find for the body which is of composite section subject to a different cross section, Young's modulus, and also the lengths are also varying. So you can find the corresponding value of the change in length in individual part 1, part 2, and part 3. So delta L is equal to delta L1 plus delta L2 plus delta L3, provided all are subject to a tensile force. If any of the section is subject to compressive load, the decrease in length will be taken place. For example, for the second and third part, we are getting a decrease in length means delta L is equal to delta L1 minus delta L2 minus delta L3. So based on the net force acting on individual section, by using the free body diagram concept, we can able to find whether it is an increase in length or decrease in length. So accordingly you can modify the corresponding value of the change in length of the given material of single material of the body, or different cross section, different length of the body. You can definitely find the total deformation of the body. Thank you very much for patient listening, and goodbye. Thank you very much.